Hello. I've been working on this project for about 5 years. It's not 5 years of work, it's just I started buying parts 5 years ago. I started with a Commodore 64 keyboard and picked up two different commercial products to make them USB. Why did I need two USB boards? Well, that's what we're going to look at in this video. We're going to take apart a VIC-20, look at the history of keyboards, run a circuit simulation of a matrix decoder, test out the firmware in the boards I bought, and build the best Commodore emulation keyboard ever. We'll be testing this keyboard in both Vice software emulation and on an FPGA project called MiSTer. Oh, and there's some 3D printing too. Let's start by testing a Commodore 64 keyboard in situ. This gives me a baseline for things we can measure. It also gives me inspiration and a sense for the attributes that are difficult to quantify. This newer style of the 64 has the graphics symbols on the tops of the keys instead of the side, so it's easier to show on camera. However, the keyboard internals remain unchanged since the VIC-20. All of the 8-bit Commodore computers used a character set we call PETSCII. Commodore's first computer was called the PET. At the time it was designed, ROMs had become cheap enough to include a full ASCII character set. But users wanted graphics characters instead of lowercase letters, so the extra space was used for these symbols you see on the keys. In retrospect, lowercase would have been a better choice, but if you look at the period, it's easy to understand the decision. The telegraph system had been operating just fine for 100 years without lowercase. In fact, many early computers used telegraph equipment for both input and output. This is the Teletype Model 33 that came out in 1963. I remember playing with one when I was about 7 years old. It was long retired at the time, and I suspect it had never once been hooked up to a computer, but I got to make punch tape for the first and only time in my life. I've never even seen one of these machines since that day. This was the machine of choice for mini computers and early micros like the Altair. It was ASCII, and the paper tape was 8-bit, but the mechanism could not print lowercase. The jump from 4 or 8K of RAM up to 64K enabled a new type of application called word processing. Any computers after this point which didn't include lowercase would fail in the market. The Commodore 64 and VIC-20 came with two character sets. It booted to the original PET set, but if you press the chicken lips and the shift key, it sacrifices some of the graphics to give us this horror show. All this does is point the video chip at a different character set, so no data bits were harmed in the transformation. Let's look at the other features of this keyboard. Most of the keys have two graphics symbols. The symbol on the left comes up when modified with the Commodore key. The symbol on the right comes up with the Shift key. The colors on the numbers come up with the Control key. The Commodore key can pick another set of colors that aren't labeled. This next bit is where it gets interesting. Those symbols above the numbers are not where we expect them. The 2 has a quote. Parentheses are on 8 and 9 instead of 9 and 0, and so on. There's also the cursor keys, which require the use of the Shift key. We'll sort through all that later. Let's look at how the keyboard performs when typing fast. We can test this subjectively by looking at the rollover. If you have a gaming keyboard, it might have advertised a feature called N-key rollover. That means there is no limit to the number of simultaneous key presses that can be detected and reported to the operating system. If it doesn't have N-key rollover, then there will be combinations of keys that cannot be detected. The test is simple. Press keys, don't release them, and count. Let's go. A, S, D. Okay, that didn't go well at all. Normally, the uncertain key presses are suppressed with a technique called ghosting. I guess they ran out of ROM space, or didn't want to spend the cycles, I don't know which, but Some of you are halfway out of your seats with your hands up ready to shout diodes. Let me catch everyone else up before we go on. I want to take a better look at the hardware. Let's go to the device that this keyboard was first designed for. I bought this VIC-20 off eBay many years ago. It was super cheap and untested, but the keyboard looked clean and that's what I wanted it for. Turns out it works fine and the whole thing is in excellent condition. So let's take it apart. 3 screws and the case hinges off. Now we can see a case of form-following function, with a pun intended if you like. All that metal is a sink for a linear regulator. There's no fan and not much ventilation, so cooling leans heavily on having lots of air volume. We're here for the keyboard though. It has 18 wires and a 20-pin connector. It plugs into the main board right next to a 6522 VIA. The 6522 provides 16 GPIOs, so if you're guessing an 8x8 matrix, you'd be correct. While we're in here, let me show you how these USB boards were intended to be used. These keyboards will long outlive the NMOS chips, so you yank a failed motherboard and put them here. These joystick ports stick out the side, and so does the USB cable. But this VIC-20 case is massive if you just want a keyboard. The new Commodore 64 case takes up even more desk space. I just want a minimal keyboard. Let's part out this VIC-20. Just kidding, I'll put it back together. I have a couple of keyboards without cases, and one of them needs a new plunger. I also have a new plunger and a jar of analgesic for after I remove and replace these 500 tiny screws. Okay, here's what we have. It's definitely a matrix, and there's no other components at all. The mechanical shift lock key is in parallel with a shift key, and the restore key isn't part of the matrix at all. That explains the 2 extra wires and accounts for all 66 keys. I've heard there are variations of this keyboard, but the dozen or so I've worked on all look like this. These are very hardy keyboards, but a lot end up missing the corner keys from decades of being shoveled around with other forgotten toys. Now that we know for sure what we're dealing with, let's play with this in a circuit simulator. The basic idea is that you send current down a column and read the row data, or vice versa. The rows all have pull-down resistors, and the columns float with only one driven high. We can do all this in software. All the logic around this matrix is only to drive the simulator. Let's look at what happens when you press a key. I used toggle switches here, but of course they are push buttons on a real keyboard. As the columns are scanned, we can see the key is detected. Current moves from the column to the row. We can even detect multiple keys at once. In a row is no problem. A column works fine. And so does diagonal. The problem with ASD is something else. A right triangle. Pressing 3 button, this is detected as 4. Most matrix decoders will detect this condition and suppress the uncertain key presses, the aforementioned ghosting. The Commodore 64 and VIC-20 will not do this. Reading the keyboard is quite expensive for a 6502 at 1 MHz. It's done 60 times a second whether a key is pressed or not. Fortunately, my goal is only to make a USB keyboard, so we'll have an entire microcontroller and no need for compromise. Let's look at what's happening. Okay, it's pretty obvious 2 columns are being selected. The buttons are powering up a column that shouldn't be. This is where some diodes would come in handy. If you put a diode in series with every button, this backfeed of power can't happen. Commodore didn't do that in order to save money. Some keyboards are still made like this today, but have the matrix set up better so you don't notice. I'm not going to add diodes, it's not needed for emulation. So far, the 2 big things I see are remapping the keys and handling ghosting. How about we test out these USB boards and see how they perform at those tasks? No, this won't do. This is going to drive me nuts. I've had some time to think about packaging. Let's make this keyboard stand proud. It needs rubber feet, the correct angle, and perhaps some of the bread bin aesthetics. I don't design parts often enough to remember a GUI, so I use OpenSCAD. I made this foot, and these rounded pieces will cover the screw holes. There's nothing special about the slicing, just the defaults. And then I wait. Let's put this together. We start with the feet. These rubber bumpers will provide a solid footing. One side is held with a screw, and the other side gets an interference fit. I added some acrylic tape to make sure it never develops any kind of wobble. This feels nice. The angle is good, and it's more solid than it could be in a case. And now the trim pieces. These are held in with only tape. If you think this tape won't hold, it's only because you haven't yet worked with it. There. Wow, that looks great. I mean, sure, it could be better, but for the effort I put into it, it looks great. Now we can try these USB boards. Both of them have two modes, one for emulation and the other for working with the host operating system. Let's call that ASCII mode. The emulation mode is only for Vice. MiSTer uses its own key map, which doesn't work with either of these boards. Yes, I know you can change the global MiSTer key map, but that isn't enough. I'll show you later. Neither of these boards claim to work with MiSTer, so I'll only test them where they were advertised to work. Let's first take a quick look at how Vice handles a regular IBM ASCII keyboard. There's two schools of thought. One is that the characters on the keys do what you expect. If you push a key with the @ sign, you get an @ sign. This is called a symbolic mapping. The positional mapping ignores what the IBM key says and does what the Commodore key in its position says. So typing Shift-2 gives a quote, not an @ Using a real Commodore 64 keyboard isn't so well defined. You'd think since the keyraw has a special mode just for Vice, it would map right onto one of these default positional or symbolic mappings, but it doesn't. You have to load a custom key map. It's no big deal, just unexpected. The only problem I found with the mapping is that Commodore RunStop will bring up the Windows Start menu. This is the keystroke I'm used to for loading a game, so that's annoying, but you can use Shift RunStop instead, I guess. Let's check out the ghosting. Okay, wow, the keyraw is suppressing the ghost keys. This seems to keep the Commodore software from getting confused. Very nice. If you move the switch here, the keyraw goes into ASCII mode. The wiki calls it everyday mode. I assume that means the keyboard will be useful for doing things like updating the host operating system and downloading software. Let's try it in Notepad. Hello World in BASIC seems reasonable. Okay, that's an @ let's check the instructions. There's no translation table here. What about the wiki? There we go. All right, so it looks like Shift equals is the quote. Ah, there it is. Okay, yep. And, it just goes downhill from there. @ prints a / star is a semicolon, plus is an equals. Shift 8 and no, Shift 9 and 0 are the parentheses. Okay, I'm never gonna remember all of that. It just seems like they picked random things to put everywhere. Let's just move on to the other board. This board comes from Timemouth software. It uses the same key map as the keyraw, and it even has the Same annoying Windows Start menu issue, but other than that, it works fine. Let's see how they handled ghosting. Okay, that's a choice. They send the ghosted keys, and I guess that gives us a more authentic experience. What about ASCII mode? Okay, that looks good. For the most part, the keys are pretty close to what I would expect. I can live with that. Now, what about ghosting? Okay, well, they didn't do anything with ghosting here. I can understand choosing not to ghost in emulator mode, but why not ghost in ASCII mode? Well, I'm not smart enough to remember the key route mappings between sessions, and I'm not coordinated enough to work with the lack of ghosting on the Timemouth. I'm not happy with either of these. Maybe my expectations are way out of line. Perhaps this problem is so complicated that it can't be cleanly solved. Vice works fine, but neither of the ASCII modes are what I consider usable. Before we move on, I should mention the price. The Kira was about $50 after shipping. The Timemouth is 60 euros plus shipping. This next solution is only $4. I found some open source software on GitHub for the Pico. It only supports MiSTer, but that's okay. Unfortunately, I never did get it running. I was updating it for the latest SDK when I noticed it was driving all the columns simultaneously. One column would be driven high and the rest low, which would blow out your GPIOs if you held down two keys in the same row for too long. It was obvious there were other problems as well. It's just an example from the USB library they used with a lookup table added, so no big loss. I had mostly finished with my own implementation when I found this anyways. The first iteration of mine is similar enough to show the mapping problems it has, which I'll get to in a moment, right after I glue this Pico to the keyboard. Alright, no project achieves success without a little blood sacrifice. So this first iteration is just a straight-up remapping of the key codes. Positional remapping, if you like. The GitHub project I just showed had a few lines of code to help navigate the MiSTer menu, which I'll do later in a different way. Other than that, and the exploding GPIOs, it'll behave the same. The main problem is the symbols over the numbers. Shift 2 comes up with a quote, which is correct. But Shift 6 should be an ampersand. It's an apostrophe. Shift 7, which is an apostrophe, comes up as an ampersand. Shift 8 and 9 should be the left and right parentheses, but it's an asterisk and the left parentheses. This also shows the problem with using the global key map on a Kira or Timemouth board. There's no way to get the shifted numbers to work right. Not that I found anyway. Anyhow, a positional remap like this is a good start. But before I begin remapping symbols, I want to add ghosting. Back to the simulator, let's figure out how we can detect ghosted keys. Okay, so the third key press instantly jumps to 4 key presses. We don't know which corner is real, but we do know that 2 key presses is always valid. Actually, 3 key presses is always valid too. It's only when 4 are detected that there's a problem. Okay, that's pretty simple to implement, and it'll work. Some development methodologies would have you implement this first and improve it later if needed. Fortunately, I'm the boss here, and I say let's do it right the first time. There's a precise way to know which keys need ghosting and which don't. It took a whopping 2 minutes to figure out. Here I'm setting up 4 key presses. The first 2 work fine. The third key press needs ghosting. And this 4th key press should be detectable. Before we consider a key press valid, we need to ask, is this key participating in a right triangle of key presses? We can search its row and column, and if there's other possible key presses in both directions, we have detected a ghost key. But searching a grid isn't the answer. That's way more work than needed. It's much easier to keep a population count of the rows and columns. We can do this while scanning the keyboard and keep the time complexity close to 01. So now, if you want to know if a key should be ghosted, you just look at the row and column populations. If both are greater than 1, you have a ghost. My next iteration did this. Here I'm pressing 4 keys at once. And the ASD case works too. In fact, if we release either the A or S first, which is what will happen when typing normally, the D will be detected. But there's still a problem. I'm going to hold A and S and repeatedly press D. Uh-oh, something went wrong. Back to the simulator. Here's what's happening. The third key is pressed in the middle of a scan. I'll step through it manually. There, this third press shows up wrong, but won't be detected as a ghost because we don't see any other presses in the row. We need to make another pass to detect the ghost. Now you may be thinking, this happens so fast, I shouldn't have been able to demonstrate it so easily. But these keys bounce a lot. To solve this, I delay new key presses for 2 milliseconds. I'm doing 5 scans per millisecond, and the 2 millisecond delay was determined from testing. That should give you an idea of just how much these keys bounce. Okay, that's solved. We've defeated our lack of diodes. Now it's just a matter of remapping the keyboard. Instead of a simple mapping of this key to that key, I remap the keys in their modified state. So there's effectively 2 maps, one without the shift key and one with. And both the key code and shift state is remapped. I started by making my ASCII mode. It's not very interesting. The symbols on the keys do what they say. The Sterling and Restore keys do the ASCII symbols that don't exist on this keyboard. All of ASCII is typable, and I don't need a cheat sheet. Now we need another mode for Vice, like the Kira and Timemouth solutions have. Wait, no we don't. That makes no sense. Vice just needs a key map for this mapping, so I made one and it works. Also, the Commodore runstop is no longer intercepted by Windows. However, we do need another mode for MiSTer. Pressing Control, Left Shift, Right Shift, Sterling switches modes. Yes, that's 4 keys. Nobody will be hitting that by mistake. So that's everything. 100% Vice, 100% ASCII, and 100% MiSTer. This video is running long, so I'm going to skip showing Vice and MiSTer. Full proof of both would need over 250 key presses. But there is one more thing. The reason I needed a great ASCII mode is because the Pico computer is ASCII. So let's play. Thanks for watching, and Happy New Year!